Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the Fermi level and Fermi function. Let's start. By the time you finish this lesson, you will learn the Fermi level and Fermi energy, Fermi function diagram, and the calculation of the charge carrier concentration. In the previous lectures, the concentration of the charge carriers, electrons, and holes was discussed, and we were able to calculate the concentration of intrinsic carriers using this equation. In this lecture, I want to discuss the calculation of the charge carrier concentrations in more detail. For this, we need to familiarize ourselves with the Fermi level and Fermi function concepts. Here is the energy diagram for an isolated silicon atom at absolute zero temperature. I can draw an imaginary line and say below this line all the states are occupied, and above the line the probability to find empty states is high. Of course, for an isolated atom, this is simple to say above or below the imaginary line how the states are occupied or not. However, for interacting atoms, this is not that simple. Here is the energy band diagram of an intrinsic semiconductor. In an intrinsic semiconductor, the Fermi level is located very close to the center of the energy gap, but not exactly at the center. For an intrinsic semiconductor, the Fermi level is shown by E sub Fi and can be calculated using this equation. Generally, in an intrinsic semiconductor, Nc and Nv, the concentration of states in the conduction and valence bands are not equal to each other. However, they are relatively close numbers. For example, in case of an intrinsic silicon, Nc and Nv are 10.86 times 10 to the power of 19 and 3.1 times 10 to the power of 19 at room temperature respectively. As a result, in this equation, Kt over 2 times the natural logarithm of Nc over Nv is a small number compared with the first component of the equation. The first component of the equation is the middle point of the energy gap. At the Fermi level, which is in statistical thermodynamics is known as the electrochemical potential, the probability to find electrons is 50%. By moving further below the Fermi level, the probability of finding states occupied increases, and by moving further above the Fermi level, the probability to find occupied states becomes smaller and smaller. This description is originated from the Fermi function. The Fermi function demonstrates the probability of states being occupied at a given energy level. In this function, if E equals EF, the Fermi level, the function yields half. If E is much larger than EF, it yields 0, and if E is much smaller than EF, it yields 1. You may say, hold on a second, how come that we could say the chance to find an electron in the energy gap is 50%, however, no electron can exist in the energy gap? This is a brilliant question. We need to distinguish the probability from the population. The population of states at a given energy level is the product of the Fermi function and the density of states. Since the density of states in the energy gap is always 0, therefore there is no electron population can be found in the energy gap. When working with the Fermi function, you need to distinguish the Fermi level from the Fermi energy. The Fermi energy is simply the Fermi level at the absolute zero temperature. Here I want to plot the Fermi function at 3 different temperatures. First, imagine that the temperature is 0. The Fermi function becomes a step function. For any energy below EF, the Fermi function returns 1, and at EF, it returns half. At absolute zero temperature, the Fermi function is 0 for any energy above EF. At a higher temperature, the Fermi function diagram looks like this. At EF, which is the Fermi level, the Fermi function output is half. Above the level, the Fermi function output exponentially reduces and finally ends up at 0. Below the Fermi level, the Fermi function output increases exponentially and saturates at 1. If the temperature gets even higher, the width of the Fermi function transition becomes larger and therefore giving more chance for electrons to be found in the conduction band. But why the chance of electron existence in the conduction band gets higher at higher temperature? This is because the area under the Fermi function curve in the conduction band region gets larger. In an N-type semiconductor, the Fermi level shifts up and gets closer to the bottom of the conduction band. In a P-type semiconductor, the Fermi level shifts down and gets closer to the top of the valence band. In heavy doped semiconductors, the Fermi level can even go within the conduction or valence bands. If the Fermi level is known, the concentration of electrons and holes in an intrinsic or doped semiconductor can be calculated using these two equations. And if the concentration of the charge carriers are known, the Fermi level can be calculated via these equations. In this lecture, I introduced the Fermi level, energy, and function, and we learned how to calculate the concentration of charge carriers. In the next lecture, I'll cover the majority and minority charge carriers in extrinsic or doped semiconductors. Thanks for joining this lecture of Peacademia.